Mesh analysis, which is also known as mesh current method or loop analysis, is a circuit analysis technique used to determine unknown current values in the planar circuit by what? Applying Kirchhoff's voltage law. Number one, you're supposed to identify the meshes in the circuit. So when you're given a simple circuit and you have to perform mesh analysis, first of all, identify the meshes. For this particular circuit, we can see we have three meshes, one here, two here, and the third one here. Remember, the difference between a mesh and a loop is that a mesh cannot have a sub loop in it, whereas generally a loop can have a sub loop inside of it. For example, this is a loop, and then there's a sub loop in between it. So a mesh is a standalone loop, so to say. Okay, so the first thing is to identify the meshes in the particular circuit. For this planar circuit, we have one mesh here, there's another mesh here, and this mesh here. So there are three. The second thing you're going to do is to assign the mesh currents. So for this one, for example, let's assign what? This as a mesh 1, mesh 2, mesh 3. We also have to take into consideration when assigning this mesh that we take what? Either a clockwise direction or counterclockwise direction. So you have to use one and be consistent with the particular one. So if you're using counterclockwise, you maintain it. If you're using clockwise, you actually maintain that direction. So for this circuit, let's just maintain the clockwise direction. So for the first mesh, I'm assigning my mesh current. So I call this one I1. I call this second one here I2, and the third one here is I3. So with this in mind, I can then move further. The next thing is to write the Kirchhoff voltage law equation. So you write an equation around each mesh considering the voltage drop on each element. So for first, do the for mesh 1, mesh 2, and mesh 3. So for mesh 1, forming the Kirchhoff voltage law equation, you can see that what the supply here is equal to what the voltage drop in all other elements. Since Kirchhoff voltage law states that the algebraic sum of voltages should be equal to 0, that means the voltage supply here should be equal to the voltage drop on other elements. So I'm forming the equation straightforward. So therefore, we say considering that the 10 volts here is the same thing as what the voltage drop on resistor 1 ohm resistor, which is was I1 times 1 ohms from voltage equal to current over resistance. You can see therefore that this is what 1 I1. For this particular voltage here, it is what plus what 3 I1. For this particular one, it is what 2 I1. But we also have to take notes because they said this algebraic voltage that gives us 0. So we also see that what this 2 ohms resistor is taking is also influenced by this current flow in this mesh 2. So we have to consider that. So we subtract that from the equation. So it is what 2I2. Also, this 3 ohm resistor is also taking is also influenced by this I3. So we also take that into consideration. 3I3. So I can just form the like terms here. This will give us 10 is equal to 1 plus 3 plus 2 is 6. So it is 6 I1 minus 2 I2 minus 3 I3. This will give me the first equation. Mesh 2 is using Kirchhoff's voltage law. You can also say that what the 5 volts here is the same thing as what voltage drop across all this. This is what 2 I2 plus 5 I2 plus 4 I2. So we also have to subtract that of the influence coming from what the I1. So it's on this 2, so you can see minus what 2 I1. Then that of from I3, so minus what 5 I3. So if I take my like times, 2 plus 5 plus 4 becomes 11 I2 minus 2 I1 minus 5 I3. call this equation 2. So I form the next equation for mesh 3. Do the same thing, we have 4 volts is equal to what voltage drop across these other components. So it also gives us what? 6I3 plus 3I3 plus 5I3. Then we also have to consider that this 3 is also sharing current with mesh 1, so it is minus what? 3I1. And also this 5 is taken from I3, so it's also what? Minus 5I2. So take like times, I'll end with what? 3 plus 6 plus 5 will give us 14I3 minus 3I1 minus 5I2. This gives us equation 3. So rearrange this first equation will give me 6I1 minus 2I2 minus 3I3 is equal to 10. Second one will give me what? Minus 2I1 plus 11I2 minus 5I3 give me 5. The same vein, the last one here will give me minus 3I1 minus 5I2 plus 14I3 should give me 4. So with this, we can actually form the matrix for this particular equation. Although you can solve this directly using simultaneous equation to get values for I1, I2, and I3, but then we can as well use matrix, form a matrix out of it, from which you can use determinants to resolve it. So if I'm forming a matrix for this, I'm just going to write this out. This will give us 6 minus 2 minus 3 minus 2, 11 minus 5 minus 3 minus 5. Then we have 14. So of course we're going to bring out our I1, I2, I3, which is now equal to the value of our voltage. And very quickly you can see we just came out with our equations here, isn't it? So this is our resistances and this is our current, which is equal to our voltage. V is equal to what? IR. So with this we can form determinants for this, from which we can then solve for I1. So first thing we have to take note of is in solving for currents I1, I2, and I3 using this matrix form method, we actually first of all find determinant of this main matrix, and then we form the matrix for I1, replacing voltage here by the first rule here to form that of I1, for I2, and then for I3. Doing that, we just quickly do that. So let's take the determinants for the main matrix to be delta naught. So I'm looking for the determinant of 6 minus 2 minus 3 minus 2, 11 minus 5 minus 3 minus 5, 14. So the determinant is what I'm looking for. I can quickly use my calculator to get this value because of time, to make this video a little bit shorter. So I'll quickly use my calculator to figure that out. So using my calculator, I'm able to resolve this, and I got the determinant for this to be 559. If you can't use your calculator to solve for determinants, I've made a video that covers how to use it to find determinants. You can just check it on the description to see how you can use a calculator to calculate the determinant of a 3 by 3 matrix. Next, I'm going to form the equation for I1, the matrix for I1. Let's call it letter 1. Here, I'm going to replace the first row here with this so that we can get for letter 1. So replacing it, what I will have is 10, 5, 4, minus 2, 11, minus 5, minus 3, minus 5, 14. Okay, so the same way I'm going to use my calculator to look for the determinant of this. So the matrix, determinant of this new matrix is what? 1, 6, 7, 7. So we'll do the same thing for that of I2. That means I'm replacing this by I'm replacing the second row here with the values of our voltage. This should give us 6 minus 2 minus 3 minus, okay, so I will now have 10 here, 5, 4, and the last row here is minus 5, 14. Okay, so I use my calculator again to find the determinant. So for this, it is determinant is 949. So again, I'm going to get that of theta 3. Here I'm replacing the last row with the value of voltage. So what we have here is 6 minus 2 minus 3 minus 2, 11 minus 5. Then we have 10, 5, and 4. So next thing, I just use my calculator to get the value. Checking the matrix, my value will now be 8, 5, 8. So quickly, how do we get the value for our I1, I2, and I3? Simple formula for I1 will be what? Dividing data 1 by what? Data 0. Well, we know that data 1 is the determinant of this equation, of this matrix. Data 0 is the determinant of this particular matrix. Starting the values we now have, the value for this is 1677 divided by 559. That will give us 3 amps. So for I2, it's going to give us change in 2 over, which is the same thing as 1949 divided by 559 is 1.7 amps. So our I3 is 858 divided by, which will give us 1.5 amps. With this, we've been able to get the mesh currents in this particular circuit. So a quick recap, just so you can understand. The most important thing you need to understand in forming your equation is you use Kirchhoff voltage law on each mesh. Now, a quick hint to know if you're in the right path. Just look at this matrix here. Discover that what the diagonals there are the same thing. You see minus 2 here, minus 2 here. The same thing here. You see one is 3 here, minus 3 here, and you can see minus 5 here, minus 5 here. So once you form your matrix, or after forming your equation, if you can see these similarities in these numbers, then you should know that you're on the right path. And if you can't get these similarities, you need to recheck your equation to confirm if you've made an error. And that will be it on this example. See you in the next one.